Okay, hello everyone. Welcome to the 10th lecture on open systems. Last week we indulged our curiosity, right? And we talked about beat trajectory formalism. I hope you found it interesting. And we ended up on this conclusion that our dynamical map can indeed be written as this average over B trajectories representing the environment. We introduced this symbol for the average over the distribution of B trajectories, and we introduced this dynamical variable Z, which probably is written down some. Oh, here it is. So you have to check out previous lecture notes to decipher all the symbols here. And once we figure out that there is this average, the analogy with average is real, it's really there. The next step would be you can push it further and check out that you also have cumulants, that quantum version of cumulants of this dynamical variable Z, which behave in analogous manner to stochastic cumulants. And we will use it promptly, this property that we found cumulants. So having said that, we satiated our curiosity to some extent. So now time to go back to the matter at hand, that is, computability of dynamical map. Because we kind of already knew that this will be something we can solve because we figure out that there is a supercumulant expansion for dynamical maps, which then enables all the things you can do to make it computable. The addition of B trajectories, averages over B trajectories, and cumulants only make it more robust, this whole picture. But yeah, computability. So we're looping back to to the idea of supercumulant series. So once you identify that you have working this formal expansion of supercumulants, right? It is a infinite series, right? So it's in of itself, it doesn't solve the issue of computability.
Sorry.
Okej.
O.
Coś pan nieźle kliknął.
Generalnie klikałem, żeby to okienko z tym wyłączyć, bo mi internet mam słaby i
A,
wideo
kamerka.
po prostu. Tak,
Okej,
tak.
zrozumiałem. Nie ten guzik pan wcisnął.
Aha,
Dobra.
przepraszam.
Nic nie szkodzi. Right, so we have this supercumulant series. It's an infinite series. Each term can be evaluated explicitly, but the whole series, you don't have a formula, closed form formula for this whole series, right? So the strategy is to develop some kind of perturbation theory that would allow you to, do some approximations to convert this infinite series into some closed form expression, which then, if you have this closed form expression, it will generate a dynamical equation for a map, which you can integrate. So it gives you a computable map. And this map you compute in this way will be a fine approximation to your target dynamical map we started with. So this is the strategy. So our task for now is to basically, talk a bit about what kind of perturbation theory we can develop here to aid us in computing our supercumulant series. Right. So this is the background. So let's get to it. So a good starting point for any strategy for approximating supercumulants is to start with talking about cumulants first. So we can say that like the first preliminary step is to is a good starting point is to basically adopt a Gaussian approximation how did they word it here, to the environmental B trajectory distribution. Just to write it down, B trajectory distribution was this funny object here. Okay, so what does it mean, Gaussian approximation? Mangle this phi. Psi. So what does it mean? So if you recall from our adventures with stochastic processes, when we first time introduce cumulants of a process, right? We're talking about approximations when you cut the cumulants on some level, right? And we discussed that when there is only the second order cumulant, you get a class of stochastic process that we called Gaussian processes, right? And when we talked about them, that they are popular in applications for various reasons. One of them is that they are very simple because you just need one cumulant to completely describe them. So Gaussian approximation for our environment is basically something that mimics Gaussian approximation for stochastic processes. That is, you obtain Gaussian approximation when you disregard all cumulants beyond the second. Okay, so we can do something like this here as well. So we have this formula which defines cumulants, right? So if we neglect all cumulants above the second order, you can write it down that the Gaussian approximation basically boils down to Gaussian approximation means that whenever you have a moment, say plus, say minus, dynamical variables, right? It could be decomposed into cumulants, but we will neglect everything except for the second order cumulants. So this will turn into sum over p's belonging to, rather than all partitions of index, of set of indices, to pairs. And one. And then once you have pairs, you go for products. But the sequences will be only of length 2. T, P, 2, Z, T, P, 1. And time ordering, because dynamical variables are superoperators, they don't commute. So this is like a formally stated Gaussian approximation. I guess the most like a robust way to state it. And the consequence of that, so if we adopt this approximation, the consequence is that the totality of information about environment entering into our description of dynamics in open system boils down, it's encoded only in this second order cumulant, right? Everything else we just discarded. So this is the totality of information that comes in. So if we check out the second cumulant, if this is the only thing that matters, So the second cumulant, so here I'm using the result from the assignment 31 from last week. So you can get the following formula. Sum over tuples. There is a trace f t2 alpha 2 f t1 alpha 1 row 0 e, trace closed. Then we have here a couple of super operators on S, alpha 2 t2, S alpha 1 t1 bullet minus t1 alpha 1 bullet t2 alpha 2 loop. Plus there is a second part where there is also this what we will start calling two-time correlation function. But because it is if you look at this, this is in general a complex number, this trace here. So there is a piece with complex conjugate of this trace. And it comes in with a little bit reshuffled super operators in S minus ST1. No, sorry. I messed up my indices. Should be T2 alpha 2, ST1 alpha 1. This is how second cumulant looks like. So you can see here that the whole information about environment is encoded here, okay, in this what I will call two-time correlation function. So this trace T2 alpha 2 T1 alpha 1 row 0 e. Oop, this funny trace. So it's a correlation, two-time correlation between this of the observables f alpha. Okay, so those observables f alpha, they come in as a, if you remember, this is how the system S is coupled to environment through those operators f. And this we can write it if we want to in terms of average over b trajectories, this correlation function. In that case, it would look like this. K21 f alpha k tk function f evaluated for psi plus at time t k and the coordinate alpha k. So in terms of this trace translates into this kind of average, b-trajectory average. And this guy, this correlation function, I just mentioned that it's I mean, and you can see it from this expression that it's a complex value function. So you can like, so you have two independent pieces, two pieces. Either you can look at it and its complex conjugate, or you can split it into real and imaginary part. And there is a value in splitting it into real and imaginary parts. So I will do it right here. So I will introduce a function of like a matrix, let's say R, which is by definition a real part of this two-time correlation. you can see how the indices, what the indices symbolize here. Those indices, right? They correspond to indices in the operators here. Rho0e, real. You can check this with some simple algebra that this can be rewritten as 1/2 of trace of anti-commutator of those two observables. Alpha 1, T1. It's a useful thing to know. So this is anti-commutator. Maybe I should state what it means. So anti-commutator, so AB, it's A times B plus B times A. Right, so it's a commutator, but plus instead of minus. That's why anti. And the other part, the imaginary part, so I will use letter I to denote it. And by definition, it will be im of the same correlation function. Rho0e. And you can check that this can also be written in quite handsome way. 1/2 again, but also I, imaginary unit, trace E, and this time a commutator. So real part is an anti-commutator, imaginary part is a commutator. That's kind of cute. And why these guys are relevant here? Well, you see, those two things, the real part and imaginary part, or this averaged commutator and anti-commutators, those two quantities are related, basically directly related to two important, physically important objects. The spectral density, one is spectral density, the other is susceptibility. What they are, spectral density, susceptibility, we will get to that later on. But the point is that those two things were basically measurable in like a standard experimental setup. So basically, when people deal with experimentally deal with some complex systems, they set up experiments that allow them to measure at least one of those two guys, or maybe both even. But since in this Gaussian approximation, all the information about environment comes from those two guys, basically, right? So you have a formula for that, but this might be very difficult to actually calculate theoretically. Maybe you don't even have enough information to do that, because maybe you don't really know what is the Hamiltonian of the environment or stuff like that. But here I come in and telling you that, okay, maybe you cannot calculate this, but at least you can just look it up what people measured for a given system, okay? And of course, to get full picture, you need both parts, both real and imaginary part, but it's not always possible to measure them like independently, but no threat, because there is very fine theorem from statistical physics, basically, that if your environment is in thermal equilibrium, okay, so thermal equilibrium means that Rho0e is proportional to E minus beta HE, right, where beta is the inverse temperature, inverse temp. So if your environment is initialized in thermal equilibrium at some temperature beta, the real and imaginary part are related to each other. So it's related by something that's called fluctuation dissipation theorem. So we have FDT. So it's like fluctuation dissipation theorem. So one of more important results from statistical physics and thermodynamics. And fluctuation dissipation theorem can be written as so the Fourier transform of this function I, but let's write it like this: du Fourier transform, I said, minus I omega u du equals I, and there is a thermal factor, as it's sometimes called, beta omega, which can be written in many forms, as you can imagine, times Fourier transform of the real part. Alpha 2, alpha 1, T0 plus U, T0, E minus I omega U du. So this is a fluctuation dissipation theorem. So what it tells us that even if you have access only to, let's say, I, which is usually the case, you use some linear response kind of setup to measure it, then if you know temperature, you can figure out what is the real part just by knowing the imaginary part. Or you can put it the other way: if you actually can have access to real and imaginary part from some other source, maybe you can calculate it, maybe you can measure them, then you can calculate what is the temperature of environment. So it's also thermodynamic information can be extracted from this guy. So this is very important. This is very important statement overall, and we will be using that later down the line when we talk about thermalization. This will come up often and will be of fundamental importance. So, in other words, within Gaussian approximation, the information about environment boils down to basically the things the fluctuation dissipation theorem talks about. Okay, this is a bottom line.
Sorry?
Yes?
Isn't it like the Cauchy-Riemann equations because we have like imaginary function?
Not exactly. This relation is because I'm Cauchy-Riemann. I was always thinking maybe it's Kramers-Kronig. It's more related to Kramers-Kronig relation, where you have real and imaginary parts, and you express one through the other. But this
it's the same.
This is the same. Okay.
Yeah.
So there are similarities, but this is a physics
Property.
not purely mathematics. Because
Okay.
this comes from the, well, if you want to know more, I have for you an assignment. Assignment 32, which is basically a proof FDT. So you can check it out for yourself. It's a fairly straightforward calculation to show where it comes from, but it will, give you answers, right? What are the mathematics beneath it? Okay, but this is again very important from physical point of view. Very important relation. It's good to know about it, and it's also very useful actually, especially when you operate within Gaussian approximation, Gaussian regime. Okay, so that's the info about environment. Okay, so now when this kind of approximation is actually valid. So there is a rule of thumb is that this Gaussianity, so cumulants beyond the second one are negligible or vanish, is either a very good approximation or even exact property for environments composed of like indistinguishable bosons. So think about phononic excitations in crystal lattices or electromagnetic field, because photons, we have photons and bosons, and this is like the quantum electromagnetic field is like one of the staple Gaussian systems for which well, not always, but in many circumstances, it actually behaves like a Gaussian system for which you have this cutoff for cumulants we wrote here. Beyond that, it's also in environments where central limit theorem kind of argument applies. So think of environments that are actually made out of, composed of many parts that are weakly affecting our system and are more or less independent of each other. So think of so to make a picture. So imagine that this is system S, this is our open system, right? And there is an environment, so E, and they interact with each other in some way. But in reality, this environment actually is made out of many pieces. So you have like interaction with each one of them in some manner, but they don't really talk to each other, right? So they are kind of independent of each other. So you don't have this kind of stuff. So in other words, you can think of formally, you can think of something that this coupling F alpha, for example, it could be more or less write it as something like sum over, say, k from 1 to some n, and you have something that looks like identity times some operator f times identity n minus k. So it's basically like the coupling is simply a sum of couplings to n different systems, which are largely independent. So you would say that the Hamiltonian would be something like, sum k to n, again, identities times some h, some local h, n minus k, right? And to finish the picture of independence, you would have to have, for example, something like this. So also the initial state for the pieces of environments is uncorrelated state. So this is something that would realize in the idea that the environment is composed of n pieces which are independent of each other and each contribute to interactions with our central system S, the open system. And each contributes quite weakly. So this is like the setup that lends itself to central limit theorem kind of arguments. If you remember, we talked about Gaussian processes, Gaussian stochastic processes. The central limit theorem was like an explanation why Gaussian processes are common. And it was like, we showed there a simplified version, which basically used the fact that the pieces are kind of independent, so that as a whole, the cumulants behave in such a way that the second cumulant starts to overpower or higher order cumulants, right? Which lends itself to this Gaussian approximation. So this kind of setup where you have environment made out of many pieces, weakly interacting with the open system, this is realized, for example, in like a bath made out of, or environment made out of, how they call it, nuclear spins in crystal lattices. Okay, so think of nitrogen vacancy centers interacting with like carbon nuclei surrounding it. Each nuclei has its like impurities, have some contribution to the like ambient magnetic noise around, and this is like this kind of thing can be modeled as a Gaussian environment, because it's like a bunch of small contributors that are largely independent of each other. So in other words, it's pretty common. Gaussian environments are pretty common in many cases. Okay, so that's why it's a pretty good starting point to start with Gaussian approximation. Okay, but this is an approximation on the level of environment itself. Okay, now what it does for our supercumulant expansion, which we want to build a theory, perturbation theory for supercumulants, right? This was like the first step. Well, to put it simply, it's okay. So now let's go to supercumulants. Supercumulants. So to put it simply, if you neglect all cumulants beyond the second, this tremendously simplifies all the supercumulants. In particular, odd supercumulants of odd order are all zero. Within Gaussian approximation, and this to achieve this, this is why we at the very beginning made this shift of the. If you remember, we started with a Hamiltonian that had interaction of this form. So there was this bare coupling E, and we shifted it. We went from E to F, which was defined as E minus the average value of E, right? And we did it to get this effect, essentially, okay? If we didn't do this shift in the beginning, we would have to do it right now, basically, or we would be dealing with floating average values of the coupling everywhere. It would just mess up all the estimations. It would be just a nuisance. So we would be forced to eliminate it anyway by doing the shift. So we did the shift because in the anticipation of this kind of effects. Okay, so we basically losing. We can get rid of a half of the supercumulants in one fell swoop, but doing Gaussian approximation. But also odd order supercumulants are also simplified. Well, they have to be simplified in some way because they have to be expressed as some kind of combination of second cumulant, because the second cumulant is the only thing that there is, right? So there has to be some simplifications. So let me write down a couple of first two non-zero supercumulants. So first two non-zero supercumulants. So L1 is zero because of the shift. L2 is actually unaffected by the Gaussian approximation because it's already given by second order cumulant. This is based on assignment 31 from last week. U. Right, so it was second supercumulant is always given by this the partial integral of the second cumulant. So cutting off higher order cumulants doesn't affect it, right? So it always looks the same. But I will use this opportunity to introduce a little bit of notational technique. So I will introduce something that's called a contraction. Okay, this is a contraction. This is a popular way to denote second order cumulants. Why am I introducing this contraction? Well, look, Z, the dynamical variables Z are super operators, right? So it matters where they are placed among other, among products of super operators, right? You cannot move them freely. So eventually we get to the point where this bracket notation just won't do, because we want to denote, okay, we have here four Z's, but the cumulant average is taken between like the fourth and the third, so and the second, let's say. So there is a gap in between. And how to denote it with just taking this bracket without moving those guys around? Well, we solved it previously by using the time ordering, okay? But time ordering is nice and all, but ultimately you want to evaluate this time ordering. But you cannot evaluate it if you cannot move around operators. So, you know, you have a problem there. Contraction allows you to denote which two Z's are cumulant, are in the cumulant without moving them around, okay? So the bracket notation has its limitations, right? But it also has its advantages, because contraction notation works only for pairs. So if you want to have a cumulant of higher order, it's just this kind of thing doesn't work anymore. You have to resort then to using brackets. So you know you have to use both conventions basically simultaneously, depending on which one is more convenient. And having said that, we have a fourth supercumulant. So let me start writing it, and I will use contractions here. But I will start with time-ordered integrations. And before I start writing, let me comment something. So let me just so that you won't suffer from a jump scare, look at this stuff going on here. So we have those different forms of writing down the dynamical map. We have this, say, original, where it's a time-ordered exponent average over B trajectories, which you can write as a time-ordered over Z's, over dynamical variables, exponent with a cumulant series. And you have a coarsely grained ordering for supercumulants. And now, if you imagine that these were numbers, or they're commuted, so in other words, the orderings wouldn't matter anymore, right? Then, just from this formula, you can immediately guess that if these were numbers, or they're commuted, supercumulants would be essentially equal to cumulants, okay? However, and you can see it kind of here, right? Second order supercumulant is basically second cumulant, right? However, because they do not commute, these do not commute, and those orderings matter. So you can like figure out quite quickly that the difference between L's and cumulants will have some form of commutators. You will have to reorder some Z's to get from one to the other, okay? And this is especially true when you work within Gaussian approximation, where this cumulant series cuts off on the second order, right? So basically, any higher order supercumulant will have to be made out of some z's with adjusted ordering, which you can always represent as some commutators. So with this like preamble, let me write down the fourth supercumulant, which can be written in the following way: ZU2, ZU1, and there's a commutator here, an advertised commutator between those two guys. And now, okay, where are the cumulants? Well, here is where contractions comes in. So you see what I mean with brackets? I wouldn't be able to write it down with brackets. It would be just complete nonsense. But now that I have contractions, I can evaluate the time ordering explicitly, and this is what I get. There are two more terms here, but this pattern that you have commutators, this is what I was talking about. U2, U1, and the second term has commutator here. Okay, and the contractions go like this. And there is a third term, third and last term. You can also like combinatorically figure out how many there will be. U1, ZU2. This one throw us a curveball. Commutator is here, and contractions are like this. Boop and boop. There is some kind of pattern here, but it's not very easy to decipher it. I just wanted to show you that the commutators are here and why we need contractions to actually do anything. All right. Before we go to break, let me say what will come up next. So even in Gaussian approximations, where you get rid of higher order cumulants, as you can see here, you still have an infinite series of odd order supercumulants, right? You go to L6, it will be some kind of mess of commutators, contractions, and stuff like that. It won't just disappear on its own. So just adopting Gaussian approximation for an environment doesn't give us a closed form expression for the supercumulant series. We still have to figure out some kind of arguments, some kind of perturbation theory that would allow us to basically, in the simplest incarnation, to cut the infinite series on some finite order, basically. This would be the simplest incarnation of this kind of perturbation theory. So in other words, we want to like figure out what kind of parameter regime is needed to justify us saying that the higher the order of cumulant, the smaller it is, and thus can be neglected in comparison to lower orders guys. And to properly justify this kind of sentiment, we have to estimate the magnitude of cumulants, which I thought would be a quite useful exercise to indulge in. Okay. Okay, so let's carry on. So we had this. All right, estimating. So, okay, so now we want to like have some justification for perturbation theory that about cutting the supercumulant series on finite order, for which we need some kind of estimation of magnitude of supercumulants. So let's call this estimating magnitude of supercumulants. So we'll be doing some rough estimations here. So don't look for mathematical robustness here. We're playing fast and loose with some stuff, just to have some kind of estimation that more or less reflects what's really going on. This is like the goal behind this kind of exercise is to basically identify what kind of parameters or scales, time scales, energy scales, what are the parameters of our problem, right? Which then compare them together and get something that tells you if this is big or this is small, right? So this is main purpose is to identify what are the parameters characterizing our problem, right? Which is a coupling between open system and environment. So let me start by like two sub points. So imagine that we have our coupling operators S and F, right? And we have this parameter lambda, the coupling strength. So just to be clear, imagine that S, F, we made sure to rescale them in such a way that they like the magnitude of Z, however you want to calculate this magnitude, is something of order 1, okay? So that lambda is the representant of the coupling strength, okay? We rescaled everything so that we can put all the information about the strength of coupling into lambda. So this is the coupling strength. This is the coupling. So when we want to say that coupling is strong, we would say that lambda is big. In compared to what? Well, that's another story. Where to compare it with what? If it's weak, lambda is small. This is what we want to be able to say. The other thing that we'll be needing to do our estimations is to where do I have this? Where is it? I lost my place. Okay. Next, introduce the time scale associated with environment. And oh my God, I was supposed to write environment here, but what came out, I don't know. And environment, whatever. Where is it? Yeah, time scale characteristic for environment. I will call this time scale a correlation time. Correlation time. The symbol I would use is T core and E, just to make sure that it's associated with environment, not with the system itself. And the idea behind this correlation time is that when you have a complex system like environment, we expect the environment to be like a huge complex system, when very complicated, right? So expect that in such a system, due to like very complex and maybe even chaotic dynamics inside this system, the dynamical variables will decorrelate over time, right? That there's like a correlation between something at that given time point with something else at some later time. This will decay as the delay between those two things are increased, right? Because of this tendency of like chaotic, complicated systems to just scramble everything inside, just because of its inherent dynamical law that is very complicated. When it gives of freedom, everything just mixes and stirs, and over time it just looks like a blob. So the way to capture this, the most robust way to capture this kind of idea of a time scale on which dynamical variables decorrelate, the most robust way to define it is to use the statistical irreducibility of cumulants. So correlation time, you can say the definition of it will be the following. So imagine we take a cumulant where there is whichever order of cumulant, but we just pick two instances of dynamical variable in it, and we say correlation time is such a time scale that when the delay between Ti and Tj is greater than this T core, the cumulant is zero. So this is an implicit definition of correlation time. So in words, what are we trying to do here? So so we take this variable zti, ztj, right? And this effect that as they move apart further, when they are close, they are very strongly correlated, right? Because that they are close, they're almost the same thing when Ti is close to Tj. Now you move them apart, you expect to see this kind of decay, the weakening of the correlations between them. And at some point, you move them far apart enough, the decay completes and the correlation disappears. And if there is no correlation between these two variables, this is the same as saying that they become independent, okay? And now, when you take a cumulants by definitions are statistically irreducible. So what it means is that when you take a cumulant of two independent variables, the cumulant is zero. It must be zero because it's statistically independent. This we discussed it in case of when we talk about stochastic cumulants, but the correspondence between those quantum cumulants we are looking at right now and those stochastic cumulants is basically 1-to-1, right? So in other words, if we imagine that moving apart variables makes their correlations weaker, and there is a time scale beyond which they become independent, this time scale would be the correlation time. And now, since cumulants can survive only when the correlations are present, so you can pinpoint the moment where the correlations disappear by looking at the cumulant, hence the definition, right? So correlation time is the effective range of cumulant. Okay, you can also look at it in this way. And it's also not only it is the way to capture the essence of a correlation time in the sense that this is a time when things decorrelate, but it would also be useful because we are actually using cumulants in our super cumulants, use cumulants inside them, right? We integrate them or something like that. So it's good to know what is a maximal range of those cumulants as a functions of time, right? This maximal range is exactly the correlation time. So this is the ideology behind correlation time. This is like a often used concept in this kind of considerations. So happy to introduce it here. So given that, so we have coupling strength and we have correlation time. We have two parameters so far. And now, like assuming that correlation time is somehow short, right? So there are some other time scales in our problem. And let's imagine that correlation time is one of the shortest. Okay, what we can do with that? So if this is the case, and now we look at the like a magnitude of some supercumulant of order 2k, right? We look at something like this. So having this information about correlation time, and we can like imagine, based on what we saw so far about supercumulants, that there will be like two main contributions to this magnitude, to two main like rough contributions to its magnitude. One will be the fact that, look, we have our supercumulant will always have this form that is like an ordered time integral, right? And what is integrated underneath it is a bunch of cumulants, right? And like this integrals, they are constrained by ordering, of course. So, it's like U1 is always smaller than U2 and so on. And they all go up to some total evolution time t, right? Like here. But the other constraint placed on them is exactly by the range of the cumulants, right? Because for example, here you have ZT and ZU, or ZU3 and ZU1, right? So not only you have this time ordering, but also you have this information that U1 and U3, the distance between U1 and U3 cannot be longer than correlation time, or otherwise this cumulant will disappear. And in other words, there is an effective range to all those integrals, right? It's not just the maximal time here. The effective range is actually set by the correlation time, because those variables cannot go too far, or the correlation time will kill them. Okay, so this is like the this kind of way of thinking. So maybe we can like symbolically write it down as one contribution would be something like this. So we would have our ordered integral and like a magnitude of some product of cumulants uj contraction, and say the product is over pairs of arguments belonging to all the time variables we have in our integral. Can write something like this. So you have because it's Gaussian approximation, so we have only second order cumulants. So there will always pairs of integral variables will be connected by cumulants in some fashion, some web of some pattern. Okay, and this will automatically constrain how far those two variables can go apart. And the maximal distance that they can go is the correlation time. All right, and you take this as a kernel of your integral, and you try to integrate it up to the time t, which is the total evolution time. So in other words, if you want to be super rough with this kind of a picture, you can say that this scales like t times t core e to the power 2k minus 1. the number of integrations, and you constrain how far they can go. So it's like you can imagine that you just have boxes that begin at 0 and end at correlation time, and you just integrate it over. Roughly speaking, you would get something like this. So that would be one contribution. The other contribution that you can see is those blasted commutators. Okay, I agitated to you that, especially in Gaussian approximation, supercumulants will be basically given as a integral, or that integral, of course, and you will have some combination of contractions, and there will be commutators involved. There will be some number of commutators between dynamical variables present there. So let's symbolically write it something like this. So this will be the second kind of contribution. So let me write it as 0 u I plus j plus 1 du I plus j, the integral. So we're just picking two relevant timings, which could be far apart, next to each other, who knows. And the thing we want to focus on under the integral would be, so this idea that we have this some uik, we have this commutator floating somewhere inside. ui plus j, ui minus some L, so this is how I want to symbolize the contribution from commutators, okay? And think about those guys is like, okay, so information number one, this is a commutator, right? So there is at the very least, this ui plus j minus ui, this has to be greater than 0 at least. So it's like bounded from bottom, because if it's if it's 0, the z, those two guys are the same because it's the same time, same z, commutes to 0, right? So they have to be different. They have to change appreciably for this commutator not to give us 0, right? So there has to be some distance between ui and ui plus j. But on the other hand, you cannot go too far because you have correlation times. So ui plus j minus ui cannot be greater than correlation time, right? So you want to go far to maximize the cumulant, the commutator, but on the other hand, you cannot go too far because the correlation time stops you because of cumulants around it. So now, if we still imagine that this correlation time is kind of short, it's short in comparison to other time scales, so you can imagine that this maximal change available to us is not too big. So, having all these things in mind, we can write the following rough estimation. So we want to take zt plus t correlation e zt. So this is like the worst case scenario. Okay, so this is like the maximum distance you can take one z from the other before the correlation time stops us. So this is like the furthest from trivially 0 commutator, let's say. But if we think that this correlation time is still small, So we can kind of like estimate this by saying, so this is like ZT plus the first term from Taylor expansion. DZT dt ZT. Okay, roughly sketching what's going on here. But now, what is this derivative? Well, it's more or less equal to ZT plus IT correlation E, and there will be another commutator, ZT, commutator with the generator of basically interaction picture, right? Because the YZ depends on time. If we allow me to jump, what was this? I had this. Oh, here it is. You see, it's like Z depends on time through, among other things, the interaction picture of coupling operators inside S, right? Which interaction picture is generated by the Heisenberg equation with Hamiltonian of the system, right? So what it tells us that this is the derivative, which is like a left-hand side of the Heisenberg equation. So you will have commutator with generator. This is a generator of Heisenberg of interaction picture. Int picked generator. And commutator with ZT. So we are stacking commutators here. Although this is commutator between superoperators, right? Don't forget that. And now this thing, ZT commutes with ZT, so this guy doesn't matter. And this nested commutator, we can rewrite it as, we can just rewrite it as ITE, correlation time, anti-commutator of generator and ZT square. This is like very rough calculation here, loose and not very precise, but we got something that we can say some stuff about. So now, so if you want to like estimate the magnitude of this guy, so you have magnitude of this ZT plus T core, ZT, roughly a magnitude of T core E anti-commutator HS T square. We already assume that the magnitude of Z is more or less 1, right? So the magnitude of this expression will be is basically given by the magnitude of this superoperator here. And how do you estimate magnitude of superoperator? By taking its eigenvalues, which for Hamiltonian we actually kind of need to know them. At least we can say it, what they are. So if we have a eigenvalues of this Hamiltonian, let's denote them like this. Eigenvalues of HS. Those eigenvalues imply eigenvalues of this adjoint superoperator. Eigenvalues are equal to HSA minus HSB. Okay, if eigenvalues of the Hamiltonian are H, then the eigenvalues of the superoperator made out of commutator of H is just difference of eigenvalues of H. You can, if you recall, when we talked about pure dephasing, stochastic map, pure dephasing, if you remember, we actually, this is what we found out there, right? That there's these are the eigenvalues of this kind of superoperators. So having this, then this guy, we can estimate it by saying, so let's take the worst case scenario. So T core times max over A not equal B of HSA minus HSB. Okay, so we take the largest eigenvalue possible, which so this has a dimension of time because correlation time, and the difference between eigenvalues, this is like a dimension of frequency. So it's like frequency times time, right? And one more touch here. One more touch. Let's define, since this is a frequency, a largest, you can say the largest frequency characteristic to the dynamics in the system alone. Okay. So this max A different than B, HSA minus HSB. If this is a frequency, then we can say it's, so let's make it equal to 2 pi divided by period, Ts, and let's call it T fast. Yeah.
This is not equal to be even important here. Because if they are equal, then the difference would be 0. Then either it would be max, or it would be 0 anyway.
That's a good point. That's a good point. All right, right. Because right. Okay. You know what? Yeah, that's true. You can take max just AB. Because it's automatically takes care of 0 is the smallest actually. So you want to find some non-zero frequency. That's a good point. That's a I'm gonna incorporate this into my notes. Right, so this is like we took the largest frequency. Large frequency corresponds to short period, so that's why fast. So this is like the fastest time scale associated with dynamics in our system. So in other words, this commutator, the extremely rough estimation of the contribution from those commutators is basically something that goes like T core E divided by T S fast, right? So you compare the correlation time with the fastest time scale, and you want something along line. Correlation time is still slow, is shorter than the shortest time scale associated with S. Okay, so having this rough estimation done, we can now take everything together and bring those two contributions together to get our final estimation for the supercumulant. So this is our supercumulant, those two contributions. So you can say, okay, so this guy scales roughly as lambda t. This comes from this contribution, okay? Lambda t times lambda times core E. So we are comparing the coupling strength, which also has dimension of frequency, with correlation time. And this is to power 2k minus 1. And we have this contribution from cumulants. So we'll have T E core, T S fast. And what is the power of this guy? My rough idea is that it's K minus 1. So there are for the, it works for the fourth order, because there is one commutator. If you go further, and I tried to find the patterns here. I went to L6, L8, and it seems like for order 2K has exactly K minus 1 commutators in it, or K, rather K, yeah, K minus 1. So fourth order, K would be equal to, yeah, something like that. It's fast and loose, but it's kind of, it seems to work. So this would be our estimation, very rough estimation, but still I gave you some arguments where it looks like that. So you can see that probably a perturbation we have in mind would be something that looks for coupling that is weak. So we will probably want to have something like this, that it's small. Okay, so the higher orders becomes weaker. And you can also augment this with separation of timescales in a sense, so that T core E is also smaller than not only TS fast, but also the total evolution time T. We use this total evolution time to actually get this first estimation, and basically have an argument about correlation time as a cutoff for integrals. So if you imagine that the coupling is weak in this sense, so comparison between lambda and the correlation time, and you think that there's a separation of time scales, so environment is much faster. What happens in environment is much faster, it's more violent than what's happening in S alone. Then you have an argument here that the higher order supercumulants should become weaker and weaker and weaker and weaker. So you can finish off by cutting them off. So this leads up, this is our argument, this is our justification for having a nth order approximation for supercumulant series. Supercumulant series, where we take the original supercumulant series, and we approximate it by cutting it off and some order n. It's n over 2 because we take 2k, just to remember that we use only even supercumulants. So this would be from this we justify this. Okay, so this is like the first step. Now, once we have this approximation, so now this is a finite number of terms. Each one can be evaluated explicitly. So this is like a fine closed form expression, closed form superoperator here, which can then generate for us dynamical equation. Dynamical equation. Dynamical equation. Dynamical equation for approximated map. So we can have a map N meaning that it's of a corresponding order as the cut on the a cut for our cumulant series. The dynamical equation in question is T0 equal to, we take our approximated series here, minus I lambda 2k L 2k T0. With initial condition, because you have to have initial condition if you talk in terms of dynamical equations. Okay, and this is like we discussed previously. This is a closed form superoperator, so this thing can be solved. It can be integrated numerically in the pinch. So this defines a computable map. And it's approximated map in a sense that now we can take it and finally do the nth order approximation. And now to the dynamical map. So we say our initial map, we approximate it with this solution to the dynamical equation, which is basically time order exponent k1 to n over 2 minus I lambda 2k integral. So this is the algorithm for finding our approximations, for applying our perturbation theory. And this is, so this solves the issue of computability. So we don't compute the original dynamical map, the source of the original supercumulant series, but we can compute an approximation to it, right? We know we can compute it because we have a dynamical equation generated by an approximated supercumulant series. Okay, so this is how we proceed with all these constructions. And that would be like the simplest approach to computability. And now you can, okay, so what else you can do? Well, the more advanced, more hardcore approach to this is some form of diagrammatic perturbation theory. So here, the central point of our approach was to simply cut the supercumulant series and some order based on arguments about its estimated magnitude. Yeah, the more advanced stuff is when you basically take those supercumulants and you figure out some rules how to represent those mathematical objects with diagrams, with pictures, right? And then you look at those pictures and you try to see some pattern that was hidden previously from you. And once you find something that looks promising, perhaps you can figure out how to take a whole subseries, infinite subseries of your whole series and sum it up and get a close expression for whole infinite subseries. This is how the Feynman diagrams are used in other theories. So whenever you have a series like this, you can represent it you may try to represent it with a series of irreducible diagrams, whatever this irreducibility means, and look at what can you do with it. Maybe you can see some patterns. If you can, maybe you can sum it up, sum up some subseries at least. This would be like a holy grail of this kind of approach, because if you can sum up a subseries, this is like incorporating terms of all orders, right? So it's like you take every order, but you discard some other stuff, but you still sum up over infinite number of terms. It's like some kind of approximation for sure. Maybe more powerful than just cutting at some finite order, who knows? But the the thing with this kind of approach, I say it's very fancy in advance because this is mindless, right? Cutting the series is mindless. You can always do this. But with diagrammatic approaches, everything hinges on how smart you are with figuring out your Feynman rules, the rules for translating mathematical expressions into pictures. And this is, and it's not only how smart you are, but also what is the context. Because if you just take some generic systems, generic supercumulants, there's probably no like special pattern in there. There has to be something extra, some extra bit, some special feature of the systems, so that when you find the correct diagrammatic rules, the pattern will emerge. Okay, so this is like more of an art form than engineering problem. There is no manual how to do it. So if you are lucky, if you are smart, if you are technically apt, you can do something like this. And it's like worth looking for if you have a real problem. It's like, but this is super advanced. No general statement can be made about it. Just the only general statement is that try to look for something if you can. So in a sense, this like finishes the so with the supercumulant expansion and all the other stuff we talked about, we're finishing with this. I feel this is like a neat toolbox that you could now just quit the lecture, quit the course, and take this toolbox with you. And you should be able to like customize it to your needs and start solving real problems with open system, with open quantum systems. Okay, so in a sense, this is like first stage is completed. Now we have a functioning theory of open system at this point. Of course, this is not the end of the lecture, because one thing for sure is that the way I structured this whole course is very different than the standard textbook approach, right? So at the very least, we are obliged to make a connection with textbook stuff. So we will do it, we will start doing it right now. But it's not just for bookkeeping to make sure that you know all the jargon or the slang used in literature, but it's also like we basically use it as an excuse to employ some perturbation theory in like more practical but still kind of generic contexts, right? And then once we do that, we get our master equations and stuff like that. We will apply this whole stuff, this whole machinery, to actually investigate some concrete issues that we would expect open system theory would have answers to, like thermalization, for example, and other stuff. But this will come in later. So in a sense, this could be seen as the end of the course. The rest is maybe extra stuff, but it's still important. Okay, it's still interesting. But this is like toolbox defined. You can take it, customize it. You should feel comfortable with time orderings, cumulants, supercumulants, and some other stuff. You should be able to do calculations on your own and solve some real issues, real problems you have. But stay tuned, because there will be more interesting stuff coming and some extra theory as well.